Hi guys, in this video we are going to start into our first section of chapter 3, and so all of chapter 3 is going to be focused on a special classification of transcendental function that we refer to as an exponential function. And so the very first stop we have to make here is just to define what do we mean by an exponential function in the first place. So as we look at this definition, it says that an exponential function f with a base b is denoted by f of x equals b to the x power, or y equals b to the x power, where it says here that b has to be a number greater than, we'll change this here, b has to be a number greater than 0, and it can't be equal to 1, and x is any real number. So the very first thing I want to kind of look at here is what is it that makes an exponential function? And so some things about it. First things first, we're going to refer to this b portion as the base of our exponent. And we call it the base because that's what we do call the things that exponents are attached to. Now with respect to what is our exponent here, what I want you to recognize is that with exponential functions, our independent variable is, as a matter of fact, up in our exponent. And so this is the first time we'll see our independent variable being up there. And then our dependent variable here is our y value. And we could say that y is really representing the value of b taken to the x power here. So with respect to this here, some things. We say that b has to be positive. So that's what we mean by b is greater than 0. It has to be positive. And then the other thing we want to acknowledge here is that b is not allowed to be 1. Now, before we go any further, we say, well, why wouldn't we allow b to be equal to 1? I want to challenge you to think about what would be true about a function if it was equal to 1 to the x power, and we plug in a bunch of different x values here, like this here. And so in each of these instances, we'd get 1 to the 0, 1 to the 1, 1 to the 2. I almost wrote a 2 there. Meant to write a 1. These would all be 1s. So with respect to exponential functions, we say that these are these functions where it's y equals a positive number that's not equal to 1 being raised to a power. And so for this classification of functions, we intend to learn a lot about their graphical behavior. And so if we're going to get into graphical behavior, then we need to just look at how do we evaluate these on a calculator. So first things first, go ahead and get your calculator out. And what we're going to look at is how do I use a calculator to help me make a table of values here. So it says use a calculator to evaluate the following exponential functions for the given values of x. So the first one here says that our function of x is 8 to the x power. We want to find f of pi. So essentially all we're really practicing doing here is taking an input, in this case pi, and then plugging it into our function, which in this case our input is up in the exponent. So we get 8 to the pi power. Could I actually do this on a calculator? Well, hey, we actually can here. So in terms of how to type these things in, remember that your caret key here is the to the power of key. And pi, for instance, is right behind our caret key. We say 8 to the pi. I would say out to about 2 decimal places here, we get 687.29. So approximately 687.29. So what I want you to do is go ahead and pause the video. And I want you to evaluate b and c here for these given inputs of x. And when you're ready to see what I end up with, go ahead and unpause the video. If you've already done your work here and unpause the video, for letter b here, we have 8 to the negative x. That means that if I make a table here and we plug in a half, then really what I'm going to get, and I think this should be g of x here, is I'm going to get 8 to the negative 1/2 power. So to type this in, you might have guessed that we have to take 8 to the power of something, but we're going to put in parentheses negative 1 divided by 2. And so it's going to take this to this 8 to the negative 1/2 power. We get about 0.35, so we get approximately 0.35 is our output value. And then for this last one here, for h of x, if we plug negative 2.5 in for x, negative 2.5, our output would be 8/10 to the power of negative 2.5. And so this is just a proof of concept that we can input x values and always get out x or y values for these things. 0.8 to the power of negative 2.5 actually comes out to be about 1.75, so approximately 1.75. So with respect to these functions, any x value you plug in, as a matter of fact, we can always raise a non-zero or always raise a positive number that's not 1 to a power and get a y value back. And so that'll be a good lead into then our graphs here. We're going to look at the graphs of exponential growth. and then we're going to compare this to what we call exponential decay and see if we can determine a general way of determining whether or not it would be growth or decay. So it says fill out the following table of values for each function, then sketch a graph of the functions. So the two functions that I've given us here, f and g, are a couple of exponential functions where in the first one our base is 2 and our second function our base is 4. So we're going to look at evaluating 2 to the x power first, and I wish I would have made a vertical table here just to be able to show some more work. But when we plug in our input variable here, or input value, remember that that's going up in the exponent. So the very first place I want to start here, and this is true for both functions, is just that this fact that anything to the 0 power is equal to 1. And so maybe we write that up over here. Fact. We'd say any number n to the 0 power equals 1 as long as n doesn't equal 0. 0 to the 0 is what we call indeterminate form. So if I raise 2 to the 0, I get 1. But what do I know about 2 to the first power? Well, I know that I should expect to get 2 here. And if I do 2 to the second power, I should expect to get 4 here. And if I do 2 to the 3 here, the third power, I would expect to get 8. Already, when I look at what is the pattern here that's happening with my y values, as x is growing bigger by 1, at least with our f of x function, what I see is that we're multiplying by 2 times 2 times 2 times 2. So one characteristic I already see of exponential functions is that these are functions that continuously multiply the last number by the value of its base again and again and again. You might suspect that if we go backwards, each of our y values would divide by 2 to get the y value that preceded it. So 8 divided by 2 is 4, divided by 2 is 2, divided by 2 is 1. So what does that help me to conclude about 2 to the negative 1? Remember that any number, we'll say n to the negative 1 power, is the same as 1 over n to the positive 1 power. And so the way I look at this negative symbol here is we're going to call it the move it symbol. But it is very true that any fraction, if you take any number's base and you move it to the other part of the fraction, so if I move n downstairs, its exponent switches its sign, and we often like to write these as positive exponents here. That just means that when we take 2 to the negative 1 here, and I'll write this down here, 2 to the negative 1 is the same thing as 1 over 2 to the positive 1. It means that I get a half here. And if I do 2 to the negative 2, the thing is that's 1 over 2 to the positive 2, that's a fourth. So one thing to keep in mind with these exponential functions is that when you raise something to a positive power, like 2 to the first and you get 2, when you raise that thing to its negative power, you just get the reciprocal of what you would have gotten had you raised it to the positive power. So 2 to the negative 2 is the same as 2 to the positive 2, but it's reciprocal. So as we paste these together or put these together down here for 4, we say 4 to the 1, that would be 4. 4 to the 2, that would be 16. And then 4 to the 3, we would get 64. So you can see that 4 to the power of x is growing much more rapidly than is our 2 to the power of x. And if we did 4 to the negative 1, remember that's the same as 4 to the 1, except for its reciprocal. And by the same means, 4 to the negative 2, we would therefore get 1 over 16 here. So what we are going to do is we are going to graph these. I'd like to do it in separate colors here. So we'll do f of x in blue, but I'm going to go ahead and put these points on. We know that 0, 1 was one of our points. 1, 2 was one of our points. 2, 4 was one of our points. And then 3, 8. So we go 1, 2, 3, 4 more up. And as we went backwards, we say that negative 1 went to a height of a half and negative 2 went to a height of a fourth. One thing that we need to acknowledge right off the bat is that no matter how far left we go on this table, if I raise 2 or 4 to a negative power and it's negative enough, I still would never get 0 for an answer. So one big theme with all of our exponential graphs is going to be that they have a horizontal asymptote on the x-axis or at the line y equals 0. And so I'm going to label this here. This is a horizontal asymptote. And an asymptote is just these values that our graph tends to approach but never quite reach. And so sketching this in, we're going to look like we're on the asymptote here. I want to be a little bit more careful. Our graph is going to go up and up and up and up and up and up, and it's just going to continue to get steeper and steeper. So we're going to refer to this one as f of x. Let's go graph g of x now, and perhaps we do this in like a greeny color. But we see that g of x also goes through 0, 1, but this time goes through 1, 4. 2, 16. I can't even graph that one. So this is going to exit very steeply. And then at -1, we're at a height of a fourth, which is half the height of this blue dot. And then we're at a 16th, which is right almost on the x-axis. So as we draw this one in, you're going to see that it looks very similar to our original 2 to the x graph, except for this thing grows much more quickly, and we'll label this g of x here. So already I can see that exponential graphs are very similar to one another. At least they have a couple of similarities. Both of these graphs have an asymptote on the x-axis, and they go through 0, 1. And so I'm going to label that point on these graphs here. This is what we refer to as exponential growth, and the way we can tell that it is growth is just simply because from left to right here, our y values are getting bigger and bigger and bigger positives. So what we're going to check out now are graphs of the form y equals b to the negative x, which is kind of a weird thing to think about. This fact that we have this positive base that's not 1 being raised to a negative power, how would that affect my functions? So again, I'm going to use 2 and 4 as our bases, but let's look at how a negative would impact this. If we did 2, and let me try to get this so that I can write on it here. That's better. If we do 2, oh, come on. I just wrote on this. If we do 2 to the negative and put in a 0 here, we still get 2 to the 0. So in this case, we'd still get 1. And the same thing for 4. 4 to the negative 0 is still 4 to the 0 is 1. But the moment I do 2 to the negative positive 1, this is the same as 2 to the negative 1. And so in this case, I would get a half. If I did 2 to the negative and then put in a positive 2 here, then I would get a fourth. Trying to write small here, and then 2 to the negative positive 3, we would get an eighth. And going backwards this time, if I did 2 to the negative 1, that actually makes that a positive 1, which guarantees I get a 2 here, and 2 to the negative 2 would therefore give us a 4. So some things. It looks like the same table we had previously, except for everything was just kind of flipped over. So if we go graph this, I'm going to go ahead and start by putting a horizontal asymptote at y equals 0 or on the x-axis, but I see that it still goes through 0, 1, except for this time it goes through 1 comma a half, 2 comma a fourth, 3 comma an eighth. It's getting really close to 0, and as we go backwards, -1 went to 2, and -2 goes to 4. So as we connect our dots here, -3 I'm going to go ahead and put up at 8. We're going to see this graph that is not increasing from left to right, but decreasing from left to right. And so this would be our f of x in this case. And g of x, by the same right, 4 to the negative positive 1 would be 1 over 4. 4 to the negative 2 would be 1/16, and 4 to the negative 3 would be 1/64. Whereas 4 to the negative 1 is 4 to the 1, that's 4. And 4 to the negative 2 would be 4 to the 2, which is 16. So what you're going to notice here is that these two graphs also come together at 0, 1. And they also have kind of the same basic shapes in terms of what they looked like in the last graph there. But in this case, from left to right, our graphs are decreasing over time. So we're going to refer to this as exponential decay. And so you can really see that the shapes of these are the same, just that they're kind of flipped over the y-axis. So one thing that I do want to indicate here is that when you have a negative in front of your independent variable here, or in front of your x, you could almost interpret this as it's going to be a y-axis reflection if we think about our transformations there. Making x negative, all of our x values, the opposites, would mean that it would flip over the y-axis there. So we're going to make some general statements about the graphs of y equals b to the x and y equals b to the negative x. Starting with this, these two graphs right here, let's go ahead and put on top of this one y equals b to the x and y equals b to the negative x. But I kind of just want to know what would be true about my parent function, which this y equals b to the x would be my parent function. So in every possible instance of our parent function here, what I'm going to ask you to do is make a table, and what you're going to see me plug in are -1, 0, and 1. With respect to why am I choosing this, it looks to me like these exponential growth and decay graphs, at least on the left here, very boring. They're getting close to 0, and on the right they just keep increasing. And if it's decay on the left, it's coming down and decreasing, but it's way up in the air, and on the right it's really boring, it's getting close to 0. So where are these graphs really interesting? We're going to say that these graphs are mostly interesting around the origin, and so we tend to, at least with the parent function, plug in -1, 0, and 1. And so I'm going to go ahead and put these in here, but we're assuming that I have b. So if I say b to the 0, I think one fact that we want to make sure that we associate with all exponential graphs is that anything to the 0 is 1. And so 0, 1 tends to be a point that is on any exponential parent function. Now as we look at this here, we say b is b to the first, and what would I get? I would get b. And the thing to keep in mind is that b is some positive number here. But let's assume that, b is some number bigger than 1. It would mean that at 1 comma b, I would be some point that's like higher up here. And so if I were to say, what would I get when I plug in -1, I would get 1 over b. In other words, I would just get the reciprocal of what I just got right here. And so I put this at about 2.7-ish, not that it matters where I put it, but this would be 1 over 2.7-ish here. So with respect to what the parent function looks like, we know that every single exponential parent function has an asymptote on the x-axis, and as far as what it looks like, it would look like this right here. And so I know we made a table, but I do want to label these. This exponential parent function would go through 0, 1, 1 comma b, and this would be -1 comma the reciprocal of whatever the heck the base is here. Okay, so how would b to the negative x be any different here? We're going to build our table again, and in the same kind of tack as we took last time, I'm going to use the same 3 central x values here around the origin, but if we did b to the -1, this would in turn make this one our b value here, and if we did b to the -0, we would get still 1, and if we did b to the +1, that's b to the -1, that's 1 over b. And so what you see is that this behavior is still kind of similar in that it has an asymptote on the x-axis at y equals 0, and it still goes through 0, 1, but its behavior switches and it reflects over the y-axis, and so we get this graph that looks like this, and to which we refer to as being decay. So what are some facts that I want to know about all of my parent functions before we start sketching these in general, or at least transformations next? Some things that I want to know are that our base should always be some positive number. We never raise a negative to some power, and that our base should never be allowed to be 1. We saw that if we allow our base to be 1, right, we would always just get an output of 1. Other things, the domain for any exponential function, this is fantastic, but these graphs span from left to right, and so our domain will always be -infinity to infinity, but with respect to these two parent functions, because they're above this asymptote that's y equals 0, we're going to say that the range is from 0 to infinity, and notice that I do not include 0 because it never quite reaches a height of 0. I should always acknowledge that they go through 0, 1, that's a fact, and the graph is always increasing if we have b to the positive x, but decreasing if we have b to the negative x. So we see this increasing in growth here, or decreasing in decay. Other things, the x-axis, or y equals 0, is a horizontal asymptote of all of these graphs, and this graph is just continuous everywhere. So in these next few videos, we're going to work on saying, well, if I know what my parent function looks like then, it's always just this table right here, then how could I maybe sketch some transformations here? So we're going to stop this video actually right here, and we'll pick up again with sketching some transformations of these parent functions.